So ready for the last thing from Chapter 5, Section 6. So we have a little result that just provides some facts about polytime reduction. So the very first fact, first and second fact, are the two that I'm really interested in, and they say that polytime reduction is reflexive. Any language is polytime reducible to itself, and that's really kind of silly. You take the function to be the identity function, and you're done. So that one, I wrote it down. It's not foolish because I'm trying to combine it with the second, but it is awfully easy. But the second one is the one I'm really interested in. Polytime reduction is transitive. So if L2 polytime reduces to L1 and L1 polytime reduces to L0, why then you have that L2 polytime reduces to L0. That is to say, the less than or equal to sign is a sensible choice here. You'll remember that we saw earlier in some of the previous examples, we saw that satisfiability is polytime reduces to clique, and we saw that graph colorability, polytime reduces to satisfiability. So what we have then, if we look at this final page, we have graph colorability, polytime reduces to satisfiability, which in turn polytime reduces to clique. And of course, you're not astonished to find, but it's in the lemma because we need to state that it's true, that graph colorability polytime reduces to clique. Okay, so that's really the one that is most interesting in this lemma that we use right away, is that we have some kind of sensible structure. Some problems are below problems, some problems are above. Some other conditions here in the lemma: every non-trivial computable language is p-hard. That is to say, if you have a language that's in p, then every language L0, non-trivial, satisfies that L0 is greater than or equal to sub p. L1 polytime reduces to L0. So my picture that I had earlier, I drew a picture earlier of all the problems, and I put the problems in p down at the bottom. Well, that's. Well, I get, looks like it has the measles here. So that's based on that line right there, is that everybody here, everybody is above a polytime problem. And then finally, the class P is closed downward if L0 is in P and L1 is polytime reduces to L0, then L1 is in P. So again, I have the P's down at the bottom. And NP is also closed downward. So the first two sentences and the final sentence are an exercise. I don't think that a person would find them surprising. They need to be stated. For the third sentence says that every non-trivial computable language is p-hard. That if you have a language in P and a non-trivial language, then L0 is greater than or equal to, that is to say L1 polytime reduces to L0. All right, so I'm going to pick an L0 that's non-trivial. So you pick an L0 that's non-trivial. This is one of these arguments where you just sort of start writing and it all works out. So because L0 is non-trivial, there's something that's a member of L0 and there's something that's a non-member of L0. And of course, L1 is an element of P. I've got to specify a transformation function giving that L1 polytime reduces to L0. So how do you do that? Why, you have to decide how to compute whether alpha is in L1. So you say, well, the point of L1 is that it's in capital P. It's in polytime computable. So alpha is in L1 can be done in polytime. So you can do the computation required for the transformation by just computing whether alpha is in L1. If alpha is in L1, then you define f of alpha to be sigma, which we already, by definition, we already know is a member of L0. And if alpha is in L1, we compute. If alpha is not in L1, then we define f of alpha to be tau, which again, by definition, is not an element of L0. So if L1 is polytime, you can do the computation of L1 sort of really without referring to L0. So trivially, we get less than or equal to. And then the other one here for the downward closure of P, you suppose that L1 is polytime reducible to L naught via the function G. And you suppose there's a polytime algorithm for determining membership in L naught. So of course, how are you going to determine membership in L1? Well, you'll say to yourself, I start with some input sigma. I'm questioning whether it's in L1. I find G of sigma, and then I do that, of course, in polytime. And then I can determine whether G of sigma is in L naught in polytime, because the whole point here is that L naught is in P. And then I just want to say the polytime function taking me to G of the polytime function G taking me to G of sigma, combined with the polytime calculation of whether G of sigma is in L naught, makes a total of polytime, and indeed it does. Of course, if you take something that's big O of n to the I, and you take something that's big O of n to the j, and you run them both together, what you get is big O of n to the maximum of ij. Anyway, it's poly. All right, so the whole deal is poly. Okay. Okay, so most of this lemma is not surprising. Most of the lemma is not difficult, not hard to see. But the second sentence is the one that is especially interesting to us. That is to say that if you think of less than or equal to as meaning less than or equal to, you're in good shape. If you think of less than or equal to as in this drawing right here, less than or equal to is nearer to the bottom, then you're in good shape. We do indeed have some kind of up and down structure here that makes sense. If you have a down and you go to an upper and then you go to an even more upper, then the lines carry. Okay, very good. All right. Let's see.